All right, welcome back again. Today we're going to be doing section 7.3, which is all about the law of cosines. So last section we did the law of sines. Now we're going to do the law of cosines, and we're going to address those other two cases of triangles that we want to solve. So let me pull up the slides and we'll get started. All right, so here's the overview. We're going to get the law very quickly, the law of cosines. Then we're going to get an important generalization. This is one of the reasons that I really like the law of cosines, is this generalization that we'll talk about. Then we'll talk about how to solve SAS triangles, solve SSS triangles, and then we'll do an application. It's actually a pretty cool application that some of you might find yourselves doing in the future. So it's kind of a fun one. All right, so if you remember, we were figuring out how to solve triangles in the last couple sections. The law of sines took care of these two cases. The law of cosines is going to take care of the last two cases, cases 3 and 4. So in these cases, what you know is you know two sides at least, and maybe the included angle. So if you know two sides and the included angle, you can use the law of cosines. If you know all three sides, you can use the law of cosines. So this is where it gets applied the most. Okay, so pictorially, this is what we're looking at. We know this information right here, or we know this information. And in either of those two cases, you can use the law of cosines to completely solve the triangle. So what is the law of cosines? The law of cosines is this equation. If you've got a triangle with sides A, B, and C, and an angle capital C opposite side little c, then this equation holds. So this is saying that c squared equals a squared plus b squared minus 2ab cosine c. And this is why it's called the law of cosines, because there's a cosine function that appears in this equation. So it's called the law of cosines. The previous one was called the law of sines because a sine function appeared in that equation. For this one, we are actually going to go through the proof because the proof is not too difficult. The proof is pretty much just one calculation. And there's a nice picture that goes along with it too. So let's see why this is true. Here we go. We're going to start by placing our angle C at the origin so that the side length, or the side B, lies along the positive x-axis here. And remember, because we're working with oblique triangles, we already did right triangles earlier. We're working with oblique triangles. There's two possible cases for the triangle that we could be working with. The first one here, where all the angles are acute, or this one here, where two angles are acute and one angle is obtuse. But what's nice is that this setup works for either case, so you don't need to even do a separate calculation. All you've got to do is center your angle C at the origin so that the side B lies on the positive x-axis, just like this. And so the rest of this calculation can be applied to either one of these triangles. So right triangle trigonometry and the distance formula yields this calculation here. So let's take a look at it here. We're going to compute this right here. We're going to compute this length. That's the idea here. We want to try to find out what this length is, c over here, or at least c squared. We'll find the square of its length. Well, if you remember the distance formula, the distance formula is basically like the Pythagorean theorem, right? And we just need to find the the difference between the x coordinates of those 2 points and the difference between the y coordinates of those 2 points. So the distance between the x coordinates of those 2 points is right here. A cosine c is this x coordinate, and b is this x coordinate. So the distance between those x values is b minus a cosine c. And then the distance between the y coordinates, let me highlight those, or sorry, the difference. I keep saying distance and difference. A sine c and 0. Hey, come here. There we go, 0. So we get 0 minus a sine c right there. Another note I'll make, the reason that these x and y coordinates are a times cosine c and a times sine c, that comes from the right triangle trigonometry, right? Because what is cosine? Cosine is adjacent over hypotenuse, and so on and so on, right? Cosine is adjacent over hypotenuse, yeah. So you can do that. And what's sine? Sine is opposite over hypotenuse. All right, now that we have that information plugged into our distance formula, we can literally FOIL everything out, distribute everything, combine like terms, and let's see what happens. So this is what we get when we multiply everything out. In fact, let me do this. There we go. When we multiply everything out there, that's the expression we get, the one that I highlighted in orange. This piece over here, let me change the color to like a pink. Here we go. When we square this, we're going to get just that. Because again, 0 might as well not even be there. So what you end up with is a sine c squared, which is a squared sine c squared. So that's what those become. But what we can do next is move things around a little bit. Let me do this right here. Go back to here. Move things around a little bit. We've got a squared cosine squared c and a squared sine squared c. Both of those terms have a common factor of a squared, so we can factor it out. And when we factor it out, we get this. But check this out. The expression in parentheses here is cosine squared of an angle plus sine squared of an angle. That's the Pythagorean identity, right? Cosine squared plus sine squared, so that's equal to 1. That's equal to 1. And then last but not least, you can kind of commute things around, move this a squared to the front. Shouldn't say not there, but to the front right here. And then we have the law of cosines. There it is. C squared equals a squared plus b squared minus 2ab cosine c. And that's the whole proof. That's the proof. Comes right out. All right, so maybe you all have kind of seen this as you were looking at the formula, or maybe you were kind of thinking of it as we went through these calculations. But it turns out the law of cosines is a very important generalization of a much more well-known theorem. So here it is. The law of cosines is just a generalization of the Pythagorean theorem, right? Remember the Pythagorean theorem, the one that everyone knows and loves? A squared plus b squared equals c squared? Well, man, that looks a lot like the law of cosines, except it's missing that extra piece, that extra term that the law of cosines has. And in fact, if we do this, if our angle C is 90 degrees, well, cosine of 90 degrees is 0. So then what happens is that extra term, negative 2ab cosine 90, gets wiped out and it's just 0. So then you're left with c squared equals a squared plus b squared, which is the Pythagorean theorem. There you go. So when you think of the law of cosines, you should think of it as the Pythagorean theorem, but generalized to any triangle. It doesn't have to be a right triangle. Remember, the Pythagorean theorem only applies to right triangles. So you have to have a right triangle to use the Pythagorean theorem. But the law of cosines is saying, hey, we can get this information for any possible triangle. So if you want to know the length of a side, for example, and you know 2 sides already and one of the angles, you can find it. You just use this generalized Pythagorean theorem. So what's interesting here is this term, negative 2ab cosine c, this piece right here, this is basically an error term for the would-be hypotenuse of a right triangle. So if you had a right triangle, this term would be 0 and it wouldn't be there. But if you do not have a right triangle, then this term appears and it's going to have some value. And what you can do is you can use this to basically see how far off of a right triangle you really are, which is kind of cool. That's why you can think of it as like an error term or an adjustment term. It's the Pythagorean theorem plus a little bit extra or minus a little bit extra to deal with the fact that you're not working with a right triangle. So if your angle C is between 0 and 90 degrees, well, cosine of that angle is going to be positive. So that means that this term will be a negative value. negative value. So what this does is, if that angle is basically less than 90 degrees, this is going to subtract some length away from the would-be hypotenuse, the would-be hypotenuse. Now, if that angle is between 90 and 180, then cosine is negative, right? So think about the unit circle again, right? Always go back to the unit circle, right? If I'm over here in this quadrant, cosine is negative. And since A and B are always positive because they're lengths of a triangle, that means that this term here is going to be a positive term. So what happens is some length is added. Some length is added to the would-be hypotenuse. And what's funny is you can actually see this right in the picture here, right? See, the right triangle would be this. But because that angle C is not 90 degrees, we're going to end up subtracting away some of that length to get. Sorry about that. Subtracting away some length to get the length of that non-right triangle. There's like the would-be hypotenuse, right? But if that angle is greater than 90 degrees, then what you end up doing is you end up adding some length, which is pretty cool, right? So, law of cosines, that's just a generalization of the Pythagorean theorem. So you're just going to add or subtract a little bit. Okay, now let's use it. Let's actually use it. And this one I'll let you try on your own before we do it together. But here we go. Let's solve the triangle. Side A has length 4, side B has length 5. Angle C is 50 degrees, and that angle is included, or is in between those sides A and B. So think about what you would do to start. Okay, now say something out loud. What would you do to start? You probably got a pretty good idea. Okay, now try to work it out on your own. See if you can solve for the other missing information, the last side length and the two angles, and we'll do it together in just a moment. All right, here we go. Well, we know two sides and the included angle, so we should use the law of cosines. The law of cosines is going to give us this. C squared equals a squared plus b squared minus that error term. And now we can just kind of fill in the information, fill in what we know. Where did it go? Right here, yeah. So we know A is 4, we know B is 5, and we know C is 50 degrees. So we can plug all that information into our formula. We'll get this. And then 50 degrees is not a standard angle, so the best we can do is approximate it. Take the square root of that result, and then go to your calculator, and your calculator will give you an approximate length of the side C, and it'll say that C is about 3.9100 units, whatever units you're using, inches, meters, feet, kilometers, whatever. All right, now we know all three sides, and we know one of the angles. Well, now we have some options. So we could actually use the law of sines, but maybe some of you are like, oh, grown, I don't want to use the law of sines. But that's okay. It's actually better in this case to use the law of cosines. So remember, here what we just found out is we found out the last side length. And if you've got three sides, then you can use the law of cosines. And we're going to see that in play in the next example too. But the other thing is this, the law of cosines is a better choice since there's no chance of an ambiguous case. So that is one of the downsides with the law of sines, is that it can give you ambiguous cases, and you won't be able to rectify those or eliminate one of the cases unless you have external information. The law of cosines does not require that extra information. So if you can use the law of cosines, you should. And that's what we're going to do right now. So if we're looking for angle A, we can recast the law of cosines as such. So this is still the same formula, but now the information has been moved around a bit, right? So now this is the angle that is in between these lengths, the angle A, and we can fill in B and C. So we know B, I'm sorry. Yeah, we know B, and we just found what C is, and we know A. What am I looking for? Oh yeah, sorry. We don't know what the angle A is, but we do know these three things, A, B, and C, the three side lengths. So this will let us solve for the angle A. Now what I'm showing here in this calculation is me trying to maintain equality as long as possible. And so what I'm doing is I'm basically solving for cosine of A. I'm starting with the law of cosines right here, and I'm just trying to solve for cosine of A. And then I'll be able to use inverse cosine to compute the value of A. So here we go. This is what I get here for cosine of A. And I starred this equation because we're going to use this equation again in the next slide, or in the next example. So we won't have to rederive this. But this gives us what the cosine is. Cosine of A is b squared plus c squared minus a squared, all divided by 2bc. And now we use the inverse cosine, the arc cosine. We take the inverse. This is what it is exactly. This is what the angle A is exactly, right? Now we go to an approximation. So we got an approximation for the side length c, which we can plug in. And we're going to take cosine inverse of that result, and our calculator will give us another approximation. So calculator gives 51.5977 degrees approximately for the angle A. Okay, now we're almost done. We've got the three side lengths. We've got one angle. We just got a second angle. Now we can find the third angle because we know that the sum of the angles is 180. So what is the angle B? It's approximately 180 minus the sum of these two angles right here, which gives us 78.4023. And there we go. That's it. Now the triangle is totally solved. Yay! Okay, next example. So let's say we know all three side lengths of a triangle, but we don't know any of the angles themselves. See if you can do this one on your own. We're in the section on law of cosines, so you can probably guess what you're going to do first. So I'll jump straight to this. Think about what you would do and say something out loud to yourself about how you would approach this. All right, now try it out. See if you can work it out on your own and see if you can find all of the missing angles. Okay, here we go. Let's do it together. We know all three side lengths. We're going to use the law of cosines, and this is where we're going to use that starred equation from the previous example. So here we go. In the previous example, we were able to find that cosine of an angle, we'll say angle A, is given by this expression. Right? Remember, we know A, B, and C, so we can fill out this formula. Now, if we want to know what the angle A is, we can use the arc cosine function, take the arc cosine of both sides, and we'll get this. Notice here we still have not approximated anything because we are told A, B, and C are 5, 4, and 7, respectively. So no approximation has happened yet. Now we go to our calculator, and our calculator will approximate this value for us. So you just plug this in, evaluate it, make sure you're in degree mode because we're using degrees, and our calculator will spit out something like this, 44.4153 degrees. There we go. Okay, next. We know that B is, oh, sorry. We can use the same formula again, but switch the angle and switch the sides around, and it'll give us that B is approximately this value, 34.0477 degrees. I didn't repeat the calculation here because the calculation is, it's virtually identical to this one right here, except now you look at cosine of B. So it would be cosine of B equals what? A squared, what is it going to be? I always forget this. So A squared plus C squared minus B squared over 2AC, if I've got it right. But you can always go back to the law of cosines, and it'll just be this again. All right, so that'll give us that B is 34.0477 degrees. And then lastly, because we know that those angles sum to 180, we can find that C is 101.537 degrees. There we go. So, law of cosines, not too bad. It's a little more gentle than the law of sines. Now, let's use it to do an interesting application. So here we go. Let's say that a motorized sailboat leaves Naples, Florida, bound for Key West, 150 miles away. So sailing out into the ocean, right? If it maintains a constant speed of 15 miles per hour, but it encounters heavy crosswinds and strong currents, then the crew found out that after 4 hours, the sailboat was off course by 20 degrees. So the question now is, how far is the sailboat from Key West at this time? How far from its destination? What angle do they need to turn the boat to correct the course? And then how much time has been added to the trip? We're going to assume that the speed remains at 15 miles per hour. So it's not varying or anything, it's just constant. And it's the same as it was. So this is a good question, right? First, what I want you to do is just kind of let it marinate in your brain a little bit. Think about it, read it a couple of times out loud, see if you could imagine a picture, and then we'll go through it together. All right, here we go. So a picture can always help. Anytime you're dealing with these triangles and trigonometry, drawing a picture can always help. So this is about what the picture looks like, and we'll see where all these pieces are coming from. So first, the first question was, how far is the sailboat from Key West at this time? Well, let me go over to this slide instead. One thing we know is that we've been traveling 15 miles per hour for 4 hours, so we've traveled 60 miles. That's what this length is right here. And in fact, the boat is right here on this picture. That's where our boat is. We sailed from Naples to that point, and we've traveled 60 miles because we were going 15 miles per hour for 4 hours. There we go. So now we know this length right here. We also know that Key West was 150 miles away from where we left, Naples. So this length right here is 150 miles. And what we want to know is, how far away are we from Key West now? So basically, what is this distance right here? This distance, the last leg here, or I should say the last side of this triangle. How long is that? How far is it? Well, we measured that we were 20 degrees off course. So we know that this included angle here is 20 degrees. Now, because we know two sides and we know the included angle, we know right away that we can use the law of cosines. So that's what we're going to do. The law of cosines gives us this. Let me highlight it here. All these pieces right here. X is what we're trying to solve for. It's labeled right here. There's X. And at this point, you can just go to your calculator, plug in these values, and it'll give you the approximation 9185.53. That's approximately X squared. Then you take the square root of that result and you get something that's approximately 95.8 miles. So what this means is the boat, which is right here, is about 95.8 miles away from Key West. There we go. So now we know how far we still have to travel. The next question was, what angle do we need to turn to correct our course? So let me erase this real quick. What we want to know is this angle theta right here. You could think about it like so. The boat is basically facing this direction. I don't know if you can see that. Maybe if I zoom in a little bit. Here we go. So the boat traveled here and it's facing this direction. Now the question is, how much do we need to turn this direction so that we'll be back on course for Key West? That's what we're trying to figure out. We need to know that angle. Okay, so let me go to the next slide here. Where did it go? Oh, yeah, okay, there we go. So now we know all three of these sides, right? We know these three sides. If we want to know this angle theta right here, it'll help if we know this angle A right here. Let me do this. If we know this angle A, then we can find this angle theta because A and theta are supplementary angles. They add up to 180. So we're going to use the law of cosines again. We're going to use the law of cosines again to find this angle right here, the angle A. So the law of cosines will give us this formula, and that'll let us solve for the cosine of the angle. And then we can use the inverse cosine function to give us an approximation for the angle itself. So the angle A is about 147.2035 degrees. Again, that's just from a calculator. Remember, make sure your calculator is in degree mode. But now that we know what A is, and we know that A and theta are supplementary angles, we can compute that theta has to be about 32.7964 degrees. And so that's the angle we need to turn the boat. So this is what you would tell the captain, right? Or you'd tell the navigator, like, all right, we got to turn the ship about 32.7964 degrees to the east to correct the course. And what we'll do is quite literally turn the boat this way, turn the boat that way. Yeah, turn the boat that way. And then drive straight, what am I saying? And then sail straight from this point to Key West. There we go. Now we can make it, right? We're not just going to keep sailing out into the middle of the ocean. All right, now the last question was, how much time has been added to the trip? You know, like we wanted to get to Key West at a certain time. How much time did we just lose here? How much are we adding on to this trip that we didn't need to add on to? Well, what did we find? Wait, hold on. Lost my train of thought here. 60 plus 95. Hold on a second. 95. Oh yeah, because we found X, right? Let me go back. That's right. 95.8. So remember, we found that length. So let me go back to this picture again. We know this length is 60. Zoom in. And we know this length is 95.8. So that's the total distance that we are now going to be traveling on this trip. 60 plus 95.8. 60 plus 95.8 is 155.8, so that's now the total distance that we're traveling. But we knew that the optimal distance was 150. That's the straight line distance, right? As the crow flies, you could say. So if we were to go straight from Naples to Key West like we wanted to, that would be 150 miles. But now we're going to be traveling 155.8 miles. So we just added 5.8 miles to our trip. So we're going to be traveling for an extra 5.8 miles. How long does that take? Well, assuming that we're still traveling at 15 miles per hour, we can just divide those two right here. 5.8 divided by 15 miles per hour gives us about 0.3866 hours, which is about 23.196 minutes. There you go. So this error in direction added another 23 minutes to our trip. All right, and that's it. So, like I said, it's kind of a fun application, right? You could imagine that this is something that some of you might even have to do in the future. And to be honest, this stuff had to be done by hand before the advent of computers. I mean, computers have not been around forever. Before computers, all of this stuff was done by hand. And what did those people use? They used the law of cosines and they used the law of sines. And then when they couldn't use a calculator, they would have to use complicated approximation techniques. So that's one of the reasons we really, really love computers now, because we don't have to do the really difficult, dirty work of computing these approximate values of sines and cosines and things like that. But that's it for this lecture. That's it for this section. So you should go start the homework right away. The next section is 7.4, and that's all about the area of a triangle. That one is actually pretty short, so it's kind of fun too, because we're going to get these other formulas for area. But I'll leave you all with that, and I'll see you next time. Have a good one.